Thanks for joining us today to cover Safety Integrity Level Simplified. So today we're going to go through a bit of an introduction and take a look at an overview of risk assessment. And then we've got an application example that we'd like to cover. And then we'll do some case studies of that application example. And then we'll show you implementation of a safety system and wrap it up. So in regards to risk assessment, one question that could be asked is, what is a tolerable risk? And of course, we're going to be covering that in further detail in the presentation. However, for now, let's just take a look at what is not a tolerable risk. And that would be an example of the Cleveland disaster in 1944 at the East Ohio Gas Company in Cleveland, Ohio, where the cause was found to be a tank seam vapor leak. And it killed and injured hundreds of people. It destroyed factories, homes, and cars. And this was the first commercial LNG plant in the United States. Now, although we've made significant strides in safety over the years, there are still many recent incidents, and our diligence is of utmost importance. Our goal in this presentation is to provide best practices in order to prevent such incidents. Now, in regards to risk mitigation and standards, there are two standards that we're going to cover in this presentation. One is the IEC 61508, which is a device level standard. And the way that this standard is structured is that for each instrument of the safety instrumented function, the development process, the hardware, and the software of each device are assessed. And then there's a system level standard, the IEC 61511 series, and that takes the safety instrumented function and assess the combination of the devices and implementing hazard operability study, layer of protection analysis, and as low as reasonably practicable studies. Now, the International Electrotechnical Commission, which is based in Brussels, has control of the IEC 61508 as well as the 61511 standards. And the 61508 standard, as I mentioned, is a device level standard, and it takes into account the safety life cycle of the product as well as the application of that product. The IEC 61511, which is for the process industry sector, takes those devices that are compliant to the IEC 61508 series and implements them and evaluates them from a safety instrumented system perspective. So as far as the safety integrity levels, let's just take a look at the simplified version of those safety integrity levels. So there are 4 separate levels, and they are essentially based upon consequence. So SIL level 4 is many deaths, SIL level 3, several deaths, SIL level 2, serious injury or death, and SIL level 1, minor injury. Now, what is a safety integrity level? Well, the definition is a measurement of performance required for a safety instrumented function. So assessing the risk based upon 61511, which is the basis of this presentation, we're going to take a look at some tools such as the risk parameter and consequence tree, the risk tolerance matrix, also the hazard and operability study table, and the layer of protection analysis table are some of the tools that can be used that we'll take a look at in this presentation. And now I'm going to pass it over to Dave to cover details of the application example.
Thank you, John. I wanted to address a natural question our audience may be asking, and that is, why do I want to bother with this? We've already implemented some safeguards at our site. Well, the bottom line is it does save lives, it prevents injuries, and prevents lost revenue and assets. On top of that, employers have an obligation to properly manage workplace risk. And using the tools that John has described and referencing these standards as the design goal, it ensures that the owner and the stakeholders are documenting potentially hazardous processes, assessing risks and consequences, as well as identifying protective safeguards and evaluating their effectiveness using, again, basically international standards. But to be clear, these standards are not law. So they don't define when a safety instrumented system or function is required. It is up to the owner. And since the standards are non-prescriptive, it means compliance is never going to be just straightforward and easy, if you will. So how much or little you do in claiming compliance to the standard, it is a personal or organizational choice. At the end of it all, if you are going to manage the risk properly, it will require some time and some effort. And the number one benefit here is that it provides your organization with a solid foundation of good engineering, of risk assessment and safety management practice. It actually protects the organization moving forward as the organization grows and prospers. We wanted to come up with an application example that to help put some details around the tools that John's going to show us. So we've selected an onshore natural gas plant. And in our example, here's on the right side of the slide, you can kind of see the layout with the production side to the left, the gas processing plant, then the transmission and distribution. And in our example, the gas wells are providing a slightly sour natural gas feedstock to the gas processing plant. Within that plant, there are some key processes, including an amine treatment unit to remove the H2S and the carbon dioxide, a natural gas fractionator to separate the hydrocarbons and the liquids out of our feedstock, and then also clean it and send it to the gas compressor to route it down the pipeline to the distribution system. We selected for our case study today the amine treatment unit, or ATU, and I think the next slide will give us a little closer view of the ATU process. So here is our ATU process. On the right side, you've got two drums, an absorber drum on the left, a regenerator drum on the right, and an exchanger in the middle. The absorber is the process that absorbs the CO2 and H2S from the sour gas. And you can see our green arrows. The sour gas comes into the bottom of the absorber and exits through the top. The amine used to absorb those components is then regenerated in a regenerator. And so that rich amine will be routed through exchanger to our regenerator. And two processes in the regenerator are used to basically clean that, regenerate that amine. One is a overhead condenser and reflux drum at the top, and then you have a reboiler at the bottom to heat up the amine, and then send it back as lean amine through the exchanger back to our absorber for reuse, again, sweetening our natural gas. You can see there's a lot of things going on here. There are a lot of variables that have to be monitored and controlled, including gas flow rate, amine circ rate and concentration, inlet gas temperature, the contamination or purity of the amine. And so again, you have a lot of operating parameters that must be monitored with process equipment, instruments, and control. And there are challenges, even with all this modern process control equipment. Some of the challenges and consequences include acid gas in the feedstock. And you can see as we look at the list here, corrosion is a common denominator. Almost all of these problems relate to either corrosion, leakage, or operating problems. And acid gas is a real common one. Iron sulfide in the natural gas, or hydrocarbon contamination in our amine, oxygen leaks enhancing the opportunity for an ignition, ammonia in the feed gas, and there are many others as well. And the photograph on the right can show you what can happen in the worst case scenario. And John, can you run through some of the risk assessment tools we have to figure out the best way to mitigate risks at our ATU?
Yeah, I certainly can. Thanks, Dave. That's a great application example for application of some case studies. So in regards to the risk assessment, the way that we're going to simplify this is we've got this hazard and operability study table, as well as the layer of protection analysis table. And those are fairly complex tables. And what we plan to do is send them through the hopper here and come down to a single table. And we're going to remove the calculations from the layer of protection analysis. To simplify it, we're just going to make some general assumptions with our mitigations of risk via the safeguards. So the way that this will work is that we've got the hazard and operability study that will be off to the left-hand side of the table, and our layer of protection analysis that'll be on the right-hand side of the table. Now you'll notice that we have to fill in some of the blanks in regards to the table, and we have failure, cause, consequence, and safeguard that need to be thought through. And let's just step through an example of how you might fill out the table. So from a failure perspective, let's say we've got high pressure failure and it's due to damage of the absorber, and that damage was caused by corrosion. So the consequence would be loss of containment and a resulting explosion. So what would we do as far as a safeguard? Well, we might implement a combustible gas detection safety instrumented system. Now, taking a look at our ATU process and our case study 1, let's just take a look at the absorber. So maybe we have a failure of leakage of the absorber due to corrosion and a loss of containment, and our assessment is an unmitigated risk rating of 9. Now, you'll see in the lower right-hand corner our risk matrix, and we are in the red or high risk in our risk matrix. Now, the way that the risk matrix works is that if you are in the low right-hand corner in the red, that is a high risk situation. And what our desire is, by taking mitigation effects and implementing safeguards, is to drive to the upper right light blue corner of the risk matrix, where things are very improbable and only minor injuries can occur. Now, you'll notice that there's a tolerable risk level through the cross section of the matrix with a red dotted line. Now, that tolerable risk level is the level at which the facility stakeholders would determine as far as their tolerability to certain instances. So in this particular case, we want to take a look at our layers of protection analysis, and we want to implement a couple of safeguards. So first, let's implement periodic inspection and a pressure measurement safety instrumented system. Now that would drive us to a rating of 7, or in a serious condition, and we're still not reaching our tolerable risk levels. So in addition to that, let's add a hydrogen gas detection safety instrumented system. And given that a gas detection system has low alarm and high alarm conditions associated with the operation of the device, that helps from both a frequency perspective with the low alarm as well as a magnitude perspective with the high alarm, driving us to a rating of 5, placing us into the tolerable risk level. Now, we can certainly add additional safeguards and may want to do so to continue to drive towards the light blue upper left corner of the risk matrix. So let's take a look at another case study on the ATU. Let's take a look at the exchanger. So if we had a failure of leakage of the exchanger, again, maybe due to corrosion, that scenario would put us at a rating of 8 for an unmitigated risk. So again, it is beyond the tolerable risk level. So what would we do as far as safeguards in order to mitigate the risk? Well, again, we could have periodic inspection and a pressure measurement safety instrumented system, and that would drive us to a rating of 6. We're still in the serious category, so that's still not acceptable. So in addition, let's add a hydrogen sulfide gas detection safety instrumented system. And again, given that it's a gas detection system with low and high alarm, that's going to help improve the frequency and magnitude and drive us into a mitigated risk rating of 4. And we will find that to be within our tolerable risk level. So in a third case study, let's take a look at the reboiler. So maybe we have a overpressure in the reboiler and it causes a fire. So the unmitigated risk rating there, again, is very high and something that is intolerable from the facility stakeholders. So the safeguards that could be implemented, again, maybe periodic inspection, and in this case, a temperature measurement safety instrumented system. And that would drive us to a mitigated risk rating of 6. So in addition to that, adding flame detection safety instrumented system, that would put us into a category 5 and put us into the tolerable risk level. And in a fourth case study here, let's just take a look at the regenerator, where maybe we have an off-specification product that could potentially cause a leak. And in this particular case, we've assessed the situation and said that an unmitigated risk would be a rating of 7. And that is, again, beyond our tolerable risk. So what might we do in order to drive to a better state? We may have a safeguard in this instance of mandating personnel in that area to make use of portable gas detection. And that would drive us into the medium range and again above our tolerable risk threshold. Now that we've taken a look at a few case studies, now we need to determine what our device level SIL certification expectations are. So we'll make use of this risk parameter and consequence tree tool. And the way that this works is on the left-hand side, we'll be working from left to right. And on the right-hand side, we're going to be working from top to bottom. So in taking a look at our risk parameters and the case studies that we've discussed, certainly there were several case studies where the death of several persons could occur. So we're categorized as C3. Next, we'll take a look at the frequency and exposure time, and I would say that we are certainly in the permanent exposure category, given that this facility is operating 24/7, and therefore we'll categorize ourselves as an F2. Then, as far as possibility of failing to avoid the hazard, well, I would say it's possible under certain conditions. I mean, we talked about the mitigation effects that could be taken, and that certainly would help our cause. So we'd be categorized as a P1 in this case. And then the probability of occurrence. And I would say in our case studies, it's slightly probable, and that categorizes us as a W2. And then following through with the consequence tree, that gives us a level of 2. Now this level is the safety integrity level of 2. So therefore, in our particular case, based upon this tool, we would like to implement SIL 2 equipment. Now, given the ATU examples, what we want to take a look at now is the safety instrumented system. Now, within the safety instrumented system, there are what's called safety functions. And these safety functions are from input device to output device. So the way that this works is if we have gas present, the gas detectors may have notification or turn on ventilation or have an emergency shutdown via the controls. And if we have a fire, the flame detector would pick that up, and then we may additionally have, for example, suppression. All of this equipment works through the controller and to an output device, and therefore it is a necessity of a safety function for the safety instrumented system. Now we're going to take a look at the as low as reasonably practicable scenario. And this is typically evaluated by the use of average probability of failure on demand. Now, PFD, simply put, is how likely will this device fail when you really need it. Now, as you can see, this calculation for the PFD average can be very complex due to many different conditions, such as the mean time of restoration and proof test effectiveness. Well, we're going to simplify this and make an assumption that our product is able to be tested by a proof test interval that is evaluating the entire device. And the way that the calculation is summarized then is whereby we only need the lambda DU, the dangerous undetected failures, and we need the proof test interval for this calculation. So that's how we're going to simplify it, is just by making some general assumptions. Now, the lambda DU is obtained by the SIL certificate of each device, and the proof test interval is obtained by the safety manual of each device. So what is a proof test interval? Well, it's a manufacturer-defined field periodic check that covers the procedure of the check, and it covers the frequency interval of the check. So the proof test interval is not a manufacturer routine production test or a one-time product validation test, and it's not optional, it's necessary in order to maintain the integrity of the safety instrumented system. The way that this proof test interval works with a perfect proof test is there is a duration of time of operation of the product, and then there is the probability of failure of demand over time of that product. And for the calculation that we will assess here, the assumption is that we have this perfect proof test, which means that we are able to evaluate all of the aspects of that product such that we know we have confidence in that product after that check when it's been in the field for a given period of time. And that provides this sawtooth diagram that you see. Now, taking a look at our ATU cases here and applying the PFD average calculation. So we're just going to take a look at a couple of case studies, and there are some general assumptions that we need to make. And so a couple of the key assumptions here are, first of all, our proof test interval, we're just going to assume it's 1 year, and that's a pretty typical proof test interval. And then we're also going to assume that the outputs simply use an ASCO 364 solenoid valve so that we can apply the calculations on the output device as well. So taking a look at our case study number 2 with an X5000 and XL toxic sensor, the PFD average from its certificate, along with the PFD average of the controller as well as the solenoid valve, the calculation gives us a 1.1 times 10 to the minus 3. And if you look in the lower left corner in the table, you'll see that our safety integrity level of 2 is maintained for this low demand mode of operation for this device. So taking a look at case study number 3, where we're making use of a flame detector. So on the FL500, and taking a look at its certificate and calculating it along with the controller as well as the solenoid valve, it provides a PFD average of 4.2 times 10 to the minus 2, again putting us into the safety integrity level 2 category, and therefore these devices are adequate for our application. And now, Dave, I'm going to pass it over to you to show the device implementation aspects for our application.
Thank you, John. Yeah, we wanted to take a moment to run through a simplified block diagram of modern fixed gas and flame detection systems before we dive into the implementation in our case study. And I wanted to basically what you're looking at now is just the input devices to a typical system. So we have gas detection devices. In the example today, we're talking about point toxic gas detectors, point combustible. Other technologies, point acoustic for high pressure gas leaks, and line of sight gas systems for toxic gases or combustible. Fire detection inputs include traditional smoke detectors, heat detectors, optical flame for our reboiler, and also manual call points, which you'll see in our example moving forward. Other inputs on modern systems will be for outdoor applications, wind direction can be very valuable, and also bypass inputs. In the event you've got technicians in an area doing hot work, testing or inspection, and that way the system will know that we've got people in the facility, again, doing hot work, and detection devices might be bypassed temporarily. These input signals are routed to a logic solver. The logic solver could be a fire and gas controller, could be a fire alarm control panel, it could be a programmable logic controller, but in all cases, these have a power source. And so that power source in many cases will be ground fault monitored and have a backup system, bank of batteries, and alternative source. That logic solver will also, on modern systems, often drive a graphic user interface. And this is what the technicians use as their point to, again, discern using an interactive facility map. What zone do we have the gas alarms in? If I have a fire alarm, where is it located? Do I have any faults that I need to act on? And do I have a historian here that I can look at the history of my calibration, of my proof tests, and so on? Really useful there. And so as the logic solver scans the input devices, it runs the status of those inputs through the operating logic and will drive output devices in the far right-hand column as required. Those include alarm notification devices, strobes and beacons, or horns and sounders, and even voice notification that actually provides a verbal evacuation or alarm type of voice notification to the team on site. If there's a fire suppression releasing system, it could be any one of the agents shown here, water or CO2 or clean agent or foam. And then the third type of output is emergency shutdown output, which could be de-energizing live circuits or actuating isolation valves or vent valves to, again, put our process into a safe state. For our ATU example, we have hydrogen point gas detectors, and we also decided that manual fire pull stations in the ATU area would be a very good idea. In our gas vent, we also have a fractionator and a compressor, and we also wanted to show how point H2S and point infrared hydrocarbon detection could be implemented along with portable gas detectors. Got a picture of that, which our technicians would have on their person when they enter our different areas of the plant. We have our optical flame detector there on the second to the right, and then far right are, again, manual pull stations for the fractionator and compressor areas. And then for executive actions, our outputs in our example here, we're going to have the horns and the strobe lights, the ESD. We did not show any suppression in our ATU example coming up. The next slide will show you how we implement those at the site. And so here's our ATU. And as John mentioned, our layers of protection included point hydrogen detection above our absorber drum. And you can see we've just shown that graphically there. In the regenerator, we have two types of gas detectors, a point H2S detector near the regenerator and the exchanger, as well as a point infrared detector for natural gas detection above our regenerator drum itself. In the reboiler area, we had decided to implement a UV-IR flame detector to monitor that combustion and fuel train around the reboiler. And of course, we have our manual pull stations, and these are located where our technicians can easily access them to, should they see a fire either in the ATU area or in adjacent space that needs to be enunciated and alarmed to our facility and stakeholders. So manual call points as well as notification devices also need to be installed, again, at key points where people can hear them, again, both in the process area and the adjacent spaces and areas in our plant. Wanted to show you that, of course, all these I/O devices need to be wired into our logic solver. And just for clarity, I did not show the cable routing up to our upper level devices on our slide, but you get the idea that everything needs to be routed back to input cards and output cards as required, again, for our logic solver to do its job and continually scan and update as required. And then don't forget, our technicians on our case study are fitted or basically set up with portable gas detectors to enable them to detect on their person any of the hazard gases we have present in our ATU area. So compliance is a big deal here, and we just wanted to have one slide to clarify that, you know, functional safety, as John discussed on the instrumented function and the system, the SIF or the SIF and the SIS, it can be only applied to a complete function, meaning a sensor, a computer or PLC, a logic solver, if you will, and an actuated device or output device. And so functional safety doesn't really apply to individual products or components. And this is kind of this next slide, or this sentence kind of characterizes that. When a product is claimed to be SIL whatever rated, what this means is that device is suitable for use in a SIL rated function. And it is necessary to go through the steps that John discussed earlier to ascertain, again, we're as strong as our weakest link, is our SIF, safety intermittent function, compliant to our design goal. And also be aware that some SIL suitable certificates for products, they may have some restrictions or there may have some little caveats. So again, be aware, out of the box doesn't mean it's still compliant to any particular level. It is not a substitute with a certificate for just demonstrating compliance to either 61508 or 61511. And be aware that if there's an unusual frequency of proof tests, for example, daily or something, it just may be impractical to consider that as a truly reasonable restriction. And so again, you may want to just be sure you're doing your homework and due diligence on that note. And at the end of it all, compliance with the IEC 61508 or 61511 requires evidence that you have a systematic method of managing risk over your process and equipment life cycles, and that your procedures around those processes are performed and documented and evaluated in an ongoing way. True compliance means that your process, and this entire process and complying with these standards, it's not just a paperwork exercise or a paperwork exercise. It actually is defining the way you manage your work. Now, manufacturers can make this project and compliance with these standards much easier. And how can they do that? By ensuring they got the right detectors available for your application. And those detectors are also provided with, like John talked about, SIL certificates and safety manuals that provide easy to use and understand and accurate PFD data, and that the proof tests are also meaningful and easy to actuate and reasonable to your project and your process and your facility, and that the certificates are up to date. And so I just did some screenshots here of basically MSAs, fixed gas and flame products, gas detection, flame detectors, acoustic detectors, and our controllers with the different certificates and agencies, and also a shot of our X5000 safety manual and our FM approval to 61508 for our FL500 flame detector. In summary, executing a compliant safety instrument system can be simplified using the tools John talked about today. And this means thoroughly identifying and documenting your hazardous operations, using those tools to define the risks and the consequences for your people, your equipment, and your operations, quantifying your organization's risk tolerance and protection layers to reduce risk to that tolerable level, and that also understanding that compliance requires evidence that a systematic method of managing risk has been applied and is being used over each of your processes life cycle. If you're going to manage risk, it will require some time and some effort, but John's tools were very useful in, again, simplifying and boiling it down to how can we get this done in a way that is manageable and simplified. As we mentioned earlier, compliance to these standards does provide your organization with a solid foundation of good engineering, of risk assessment and safety management practices. It does indeed protect the organization moving forward. Thank you for your time today, and we welcome any questions from our audience.